Hi everyone, welcome to our YouTube channel. In this video, we'll be learning about gradient descent. Now, to understand what gradient descent actually is, help me answer a simple question. What are the primary parameters involved in a linear regression model? So when we talk about a linear regression model, what are the primary parameters that we think of? We all know that a linear regression model is nothing but a straight line, right? It can also be a polynomial line based on certain tweaks, but ideally, this is a straight line, right? And what does the machine do? It finds this best fit line, whether the line would be something like this, or the line would be something like this, or the line would be something like this. Which one to choose? Which would be the best fit line? So essentially, we have two parameters, right? One is our slope, that is we call as m, and another is our intercept, or which we call as c. The equation being y equals to mx plus c. M is nothing but the slope, and c is nothing but this intercept, right? So by tweaking M and C, we find the optimal or the best fit line, correct? Yes. Now, since linear regression is all about finding the optimal M and C, that is the slope and intercept, don't you really think there should be a way to get the best values of this slope and intercept? Basically to minimize our cost function. Our cost function here would be MSE. It can be anything, but usually we choose MSE. That is mean squared error. That is y actual minus y predicted. And we divide it by the total number of points. So we need to minimize this error. This is our cost function. And this function needs to be minimized. How can it be minimized? By finding the ideal slope and intercept so that the points pass through the maximum actual points, right? Now, uh, therefore, right, we should ideally work towards a way to iteratively try out numerous slopes and intercepts to end up with the most optimal one, correct? And this is exactly where gradient descent comes into the picture. Gradient descent is nothing but an optimization algorithm that is used to minimize the cost function. All right. Now, how does it actually take into place? So let me clear everything. There are a few steps that we actually follow. Step one is the equation y equals to mx plus c, right? Or this can also be rewritten something like theta naught plus theta 1 into x, theta naught being c and theta 1 being m. All right. So this is step one. Step two, we need to find the cost function. The cost function would be a function of theta and theta naught and theta 1. Okay. All right. And it looks something like y minus y predicted, right? Whole square. Summation divided by the total number of points. All right. Now, this y predicted can also be rewritten as, this is my y predicted, right? So theta naught plus theta 1x, right? The entire whole square summation divided by n. So this becomes my cost function. This is nothing but my cost function. So cost function is a function of theta naught and theta 1 basically, right? Now step 3. So in step 1, we found out the equation of the line. In step 2, we found out the cost function, which is a function of theta naught and theta 1. In step 3, the entire process of gradient descent is to find the optimal theta naught and theta 1. So how do we do this? Comes from step 3. It starts from step 3. So first, initiate the value of theta 1 and theta naught. Initialize or initiate theta naught and theta 1, both with 0 or any value that you want. We usually initiate it with 0. Okay. Now comes the formula for gradient descent. The formula is m nu or c nu, whatever you want to take, equals to m old minus eta is the learning rate, into slope. The same is for c. M is for slope, c is for intercept. So c old minus eta of slope. So the formula is old minus eta of slope. Now let's come to each of these variables. Now what is slope to start with? We'll come to the learning rate, but what is slope? Slope is nothing but the differentiation. So we know that a quadratic function looks something like this, right? Slope means at any given point, right? Let me just change the color. At any given point, what is the slope? So this is one slope. This is another slope. This is another slope. Our main aim is to come to the bottom, to the least error. This is our least error point. Okay. So in simple words, our slope would be, let's say d cost d theta naught equals to, if I simply differentiate this particular equation, what should we get? Minus 2 by n. How does 2 by n comes into the picture? We know that. Okay, let me clear everything and then explain again from here. All right. Just remember this equation. M old minus eta of slope. All right. So ideally, what I'm trying to say is, sorry, m nu equals to m old minus eta of slope. All right. Which means we can also write as theta 1 equals to theta naught. Sorry. This would be theta 1 new equals to theta 1 old minus eta of, right, d cost slope, right, d theta 1. Similarly, we can also write the same for theta naught. Now, what is this d cos d theta 1? We knew the equation was, the cost function equation was something like this. 1 by n summation of I equals to 1 to n yi minus theta naught plus theta 1 x, right, whole square. And we need to differentiate this d cos d theta 1 with respect to theta 1. Now, how does it work? When I'm differentiating, since we have 2, what is the differentiation of d dx of x square? The answer is 2x. So this 2 comes over here, then we differentiate x square, that is x. All right. Since x is 1, our answer is 2x. Similar way, we'll differentiate this. So this 2 comes in the front, so 2 by n summation, then the entire equation. Okay. Now, this is the differentiation for the square part. Now, once we have differentiated this, we'll go with a chain reaction. So we'll see wherever we have this theta 1 term. All right. And ideally, we have the theta 1 term over here. This is our theta naught, by the way. Sorry. So we have the theta 1 term over here. So we'll also multiply it with x, right? So this is nothing but our d cos d theta 1. Okay, so this is this. Now theta naught equals to, again, theta old minus eta of d cos d theta naught. I hope this is understood, right? If you have a problem with the differentiation, either just have a quick recap of what differentiation is, how do we differentiate this function, or just think it as the source of truth, all right? So now when we want to differentiate this equation with respect to theta naught, again, the same thing will come 2 by n because we are differentiating the quadratic equation, right? So yi minus theta naught plus theta 1 x. Okay. Now, so the differentiation with respect to the quadratic term has been done. Now we again have to look into the term wherever theta naught is present. So we see theta naught without any other variable. So differentiation of theta naught is 1. It's like ddx of x is nothing but 1, right? Similarly, differentiation of theta naught with respect to theta naught is 1. So we multiply this with 1. So the answer is this. So this is my d cos. This is a delta differentiation which we are doing right now. Delta differentiation with respect to theta 1 and delta differentiation with respect to theta naught. So these are the two values that we get, right? All right. So now what we do is we put these values each time inside theta 1. Now theta 1 becomes old, right? When we want to find the new theta 1, what we do is we find the old value of theta 1 minus eta, will come to eta, and the value of this slope. And then we replace the entire value with theta 1. So this theta 1, which is the new theta 1, now becomes again old. And again, we go on and found the new theta 1. So ideally what happens is, if I see, let me just change the color of the ink. This was the error function, right? Initially, this was my theta 1, let's say, right? What did we do? We found the old theta 1 minus eta of the slope. So it probably gave a value somewhere over here. Okay. Now we went over to find the slope of this particular point. Okay. Now we updated theta 1 with this value. How? Theta 1 minus the value over here minus eta of this slope value. Whatever value we are getting, we put it, let's say the value comes over here. We put it over here. Again, we find the slope for this particular point, which can be something like this. So we again update the old theta 1 with this particular formula, theta 1, that is this value, minus eta of the slope over here. And we keep on doing this again and again iteratively till the value comes as a plateau, right? Till the tangent becomes horizontal with x-axis. So this is our strategy moving forth. We keep on iterating this process for theta 1 as well as theta naught, each at a time, not simultaneously, till we find the final value, which is the most optimal value, where the cost function is minimal. All right. Now, what is this learning rate, eta, we are talking about so long? So eta basically belongs to 0 to 1. Eta basically determines how far we can go. Now, this d cos d theta, the slope, can vary, highly or very slowly. So for example, now let me just clear everything out. When we say, let's say theta naught equals to theta naught minus eta of slope. So this slope can vary highly or very slowly. When it varies very fast, so what happens is this point juggles. So it goes from here to here, then here, then again here, then again over here. So it practically never reaches the minima, right? Therefore, the value of eta has to be optimal. Again, if I keep the value of eta very less, then what would happen is reaching this particular point would take ages. It will move here, 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 here. It will take so long to reach the minima. So if I take the value of eta as long, I mean very small, the time complexity would increase, the computation time would increase basically. If I take the value of eta as very large, the time complexity would, sorry, it might never reach the actual minima. Therefore, the value of eta has to be very optimal, and ideally it lies between 0 and 1. Okay. So this was all about the theory of gradient descent. Now let's understand how we actually work on it practically, and we'll create this gradient descent from the very scratch. Okay. So let me quickly start with the process. The very first step we do is we acquire the data, right? So data acquisition, or first is importing the necessary libraries, right? First we import numpy. We'll need nothing else. Data acquisition. So we do df equals to pd dot read underscore csv, and we'll take a salary data set. Okay. So let's see how it looks like. Okay. We do not want this unnamed column. So let me just remove this, or let me just take the years of experience and salary only. Okay. So what I'll do is df equals to df of um, years of experience and the salary. That's all. So now it looks very clean. All right. Now, what we want to do is first we want to split the data into the target and the features. So let's do it. Splitting into features and target. Okay. So X equals to TF of years of experience. Okay. And Y equals to TF of salary. Great. Now, what I want to do is I want to plot this. So I'll say, okay, I also need to import the matplotlib. It's fine. Okay. So we get a very linear line. Now, ideally, we can simply use a linear regression model, which in the backend uses gradient descent, by the way. But let's implement this from the scratch. Okay. So now, first thing that I'll do is I'll initialize the parameters, as I mentioned, M and C. Okay, so I'll say m equals to 0 and c equals to 0. All right. Now let's perform the gradient descent. So I'll keep a loop and I'll keep on updating the m new and c new. Okay. So for the loop, let's take some sort of an epoch. Let's say I'll run this loop for 1,000 odd times. Okay. So for I in range 1,000, or let's take that as a variable as well. I don't know how many times would I want to run it. So as of now, I'm just taking it as a variable, and with respect to time, the epochs might change. Let us call as epochs only. So epochs equals to 1,000. This is a variable. We can change whenever we want. So for I in range epochs, okay, let's give the equation. So y red equals to m into x plus c. Okay, this is my general equation of the uh, straight line, right? I have to calculate the slopes, the d cos d theta and d cos d theta 1. So let's write the slope calculation. So differentiation of m, let's say, equals to, if you remember the formula, it was minus 2 by n into sum of x into y minus y pred. And dc equals to minus 2 by n into sum of y minus y pred. Okay. So we are also doing the slope calculation. Now we simply want to update the values, right? So I'll only say update. And what I'll do is m equals to, this is m new basically. So m new equals to m old minus learning rate into, I also have to give the learning rate over here somewhere. So learning rate, let's say I take something as 0.001. Okay. So m equals to m minus learning rate into dm. Okay. I'll do the same for dc. The only thing is m needs to be changed with c. That's all. Okay. Now I can get the updated m and c. Okay. I can get the updated m and c. Or I can simply write print slope in is not. Okay. Okay. Um, got the point. So n is what? N is nothing but the total length of x. So let us also define this over here. N equals to float of len of x. So I get the value of slope as well as the intercept. All right, great. Now, what I need to do is I need to create this simple line. That's all. I could have also returned this line, but let me take it over here. So what I want to do is prediction. So y pred equals to m into x plus c. All right. Now let me just plot it inside a graph. So I'll say plt dot scatter x comma y. This is my scatter plot. And now I want to plot the graph. So plt dot plot. What I want to plot, if I simply plot x comma y pred, I probably won't get a linear curve. So I want to sort it. You remember the previous problem that I had actually encountered, right? So let's quickly sort it. So I'll say minimum of x. Let's just see what happens if I simply say x comma y pred. I'm expecting not a correct. Let's give the color. Okay. Let's just see what happens. Oh, we do get a line. Fine. Had we not got a line, we could have simply done a sorting. Minimum of x and maximum of x followed by minimum of y pred and maximum of y pred. So this is exactly the line that we get. So even without using a linear regression model from sklearn, we got the best fit line, right? How did we get that? By using the concept of gradient descent, right? This is the entire concept over here. Okay. And one more important thing, while doing this, I remembered I put a minus sign over here, which is probably not what I mentioned earlier in the theory. The reason I took the minus was the negative value came from somewhere over here. Let me also explain this. Um, so ideally, the equation is for both the equations, right? Uh, the equation is 1 by m summation yi minus theta naught plus theta 1 into x, right? So when we do the differentiation, right, whatever we do, let's say d cos d theta. So what happens is, the first thing, 2 comes over here, 2 by m, summation, the entire equation then, yi minus theta naught plus theta 1 x into, when I look from linear way, theta naught basically has this minus. So we multiply with not 1, but minus 1. Therefore, I say minus 2 by n. So this minus 1 can also be written as simply as minus of 2n. Again, if I do a d cos d theta 1, I'll get the same thing, right? 2 and the entire equation. So 2 by m yi minus theta naught plus theta 1 x, right? Then when I do the differentiation with respect to theta 1, when I look at linearly, I see minus theta 1 x. So basically the answer is not x, but minus x, right? So what I'm doing is I'm just removing the minus from here and I'm taking the minus over here. That is exactly what I've done over here. dm minus 2n x into this. You can see d of m is minus 2 by n or 2 by m, whatever you want to call it, into sum of y minus y pred, this is my y pred, into x. Again, d cos d theta equals to minus 2 by m. So minus 2 by m into sum of y minus y pred, y minus y pred. So I hope this entire concept is clear, both theoretically and practically, right? Great. So that's all for gradient descent. Thank you.